In today's notes, we're going to talk about group homomorphisms, and we're going to introduce one of the big and important theorems for group homomorphisms that has similar analogies for ring homomorphisms and other homomorphisms of algebraic objects. But before we jump into the notes, what I want to do is remind you of what a group homomorphism is. So let's suppose that I have a function f from g to h, where g and h are groups. G and H are groups, and f is a function. And I want to show that it's a group homomorphism. What that means is f is a group homomorphism if f of AB equals f of A, f of B, for all A and B in the group G. And I want to remind you that in the parentheses here, this operation is happening in the group G, right? AB is an element of G. While on this side, this big product, f of A, f of B, that is a product of elements in H. So that operation over there is the operation from the group H. And we've got some related ideas. We could talk about isomorphisms. It's a homomorphism, plus it's one-to-one and onto, or injective and surjective. So it's an injective or one-to-one function, and it's also surjective, which is a fancy way of saying onto. If you want to combine those both together, you could say bijective. We could also talk about an automorphism, which is an isomorphism from a group to itself. We could say that G is isomorphic to H if there exists an isomorphism f from G to H. So there's some function that's an isomorphism between them. You could do all sorts of fun things. You can show that this is an equivalence relation, so that G is isomorphic to H if and only if H is isomorphic to G, and we've got transitivity, and of course a group is isomorphic to itself, and blah, 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 blah. A couple other quick reminders. The kernel of my group homomorphism is going to be all the elements G and G, where f of G is the identity element of H, and the image of f is going to be all the H in the codomain H, where H is equal to f of G for some G in the group G. So kernels and images will be important for what we're going to talk about. In my mind, I have these pictures where I've got my group G, my group H. The kernel, here's my kernel, of f is everything that gets sent to the identity of H. So the kernel, all the stuff in the kernel gets sent over to the identity. And the image, so the kernel is a subset, it's a subgroup, in fact, of the group G. And the image over in H is this blobby set, and it's where everything in G gets sent. So it's all the stuff you can get by plugging in any element of G. And we've proved some stuff about this. Like, we know that the identity in G gets mapped to the identity in H by a group homomorphism. So H is a has as a subgroup the image of f, and G has as a subgroup the kernel of f. And one of the things that we'll show is that the kernel is actually a normal subgroup. So let's prove this claim that if f from G to H is a group homomorphism, then the kernel of f is a normal subgroup of G. So let's remind ourselves that it's a subgroup. I guess we can verify that. So we want to show that it's not empty. Well, f of the identity element of G is the identity element of the group H by a proposition we've seen earlier, which implies that the identity of G is an element of the kernel of f. And since it's got an element, that means it's not the empty set. We want to show that it's closed under the group operation of G. So let's suppose A and B are in the kernel of F. Then what I need to show is that f of AB is the identity, and that tells me that AB is in the kernel of F. Well, I'm going to use properties of group homomorphisms. I get that it preserves my operation. By the assumption that A and B are in the kernel, I have that f of A is the identity of H, and f of B is also the identity of H, and the identity times the identity is the identity. And that means that the element of G, AB, is also in the kernel, because when I applied F to it, I got the identity. So it's closed under my group operation. It's closed under multiplication in G. I also need to show that I've got inverses. So let's suppose I look at f of A inverse. What I need to show here is that this is also the identity element. Well, I'm going to deal with this, perhaps, I think we proved this actually in another theorem, that this is, yes, this is part of what we proved earlier, that f of A inverse is f of A inverse in the group H. So now this is the inverse of f of A in H. And that means that this is the identity in H, and then we apply the inverse, and H's identity is its own inverse, which tells me that A inverse is in the kernel of F as well. So we've got closed under taking inverses. So we have a subgroup. And now the last thing we want to show is that for normal, to show a subgroup is normal, we want to show that we have some options. We can show that, let's see, G A G inverse is in the kernel of F for all A in the kernel and G in the group G. So we're showing, this is essentially showing that G kernel of F, G inverse, is a subset of the kernel. And I'm doing that by an element argument. Okay, so this is what we want to show. So let's see what happens if we apply F to this element. In order for this to be in the kernel, we need to show, oops, that's not the inverse, we need to show that we get the identity back. So we've got F of GA G inverse. By the properties of group homomorphisms, but I guess by the definition, in fact, we get that this is F of G, F of A, and then it's F of G inverse, but as we saw above, that's really F of G inverse. And F of A, it turns out, is the identity because we were in the group, we were in the kernel, so F of A becomes the identity. And now we've got F of G, identity, and then the inverse of the element F of G, which just comes out, that identity in the middle cancels. So we end up just getting this element, F of G, and then its inverse, and that inverse is happening in the group H. So we get that this is the identity in H, which we're happy about because that shows us that G inverse is an element of the kernel of F. So the kernel here is a normal subgroup of the domain, which is pretty nice. One of the things that we're going to do is we're going to figure out how to make a quotient group using a group homomorphism. So so what we just showed was that the kernel of F is a normal subgroup of G. So we took care of that. And what we're going to show next is sort of a converse to that by saying that if we take a normal subgroup, we can build a homomorphism where it is the kernel. So this is some kind of converse idea to that right here. So let's talk about this map, this pi sub n of G map. So I'm going to take G and I'm going to build a function that takes an element of G to a coset in G mod n. So what do I know about N? I know that N is a normal subgroup of G. And the way this works is I take an element, G, and I send it over to whatever coset it belongs to. So every element in my group G belongs to some coset in G mod N, and I just send it over there. So what I need to show to get this converse idea to work out is, first of all, that phi of N is a group homomorphism. I then need to show that N is the kernel of pi sub n. And then I will have shown that we can build a homomorphism to make a normal subgroup into the kernel of some homomorphism, which is kind of a cool idea. So let's think about 1. We already know that G mod n is a group, and so we've got a function that takes G to an element of G to an element of the group G mod n. So we know G mod n is a group. So all we need to check is that F preserves the algebra. So we're going to check the definition of homomorphism, or sorry, F, I'm saying F, but I mean phi of n. So phi of n is a function. And let's think about what happens if we take GH. So what this gives us is the coset GH times n, but we know from one of the propositions about normal subgroups that this is the same thing as GN HN. That's actually how we multiply cosets, and that is the element, that is pi of G times pi n of H. So it preserves the group operation, and that means that it's a homomorphism. Now, I want to think about which elements go to the identity of G mod n for part 2. So in G mod n, the element E sub G mod n is just the coset En or n. And I want to think about which elements get sent to the identity coset. So let's suppose pi n of G is equal to n. What that means is that the coset Gn, which is what pi n sends us to, is equal to the subset n. And one of our propositions is that that means that G itself had to belong to n. And that tells us that the kernel is going to be our subgroup n. Of course, things in n are in the kernel, and this says things in the kernel are elements of n. So n is equal to the kernel of pi sub n. And that takes care of it. So that, I guess what we showed was that the kernel is contained in there, but of course, conversely, for the other inclusion, if G is in n, then pi n of G is Gn, and that's the same as the coset n. So we do get equality. That takes care of the other inclusion in this step right here. So that's pretty cool. We can take a group homomorphism, look at the kernel, and get a normal subgroup, or we can take a normal subgroup and build a homomorphism where that's the image. Where that's the kernel. One of the things you can use the kernel to do is to check whether or not a homomorphism is one-to-one, and that's what lemma 24.4 does. So lemma 24.4 says that our homomorphism is one-to-one if and only if the kernel is just the identity element. So we have a subset here, but we actually could just use the equality because the identity is always in the kernel, and so now we're saying that the kernel really is the identity element. There's nothing else in there. And that's a kind of cool result that I will let you explore on your own. All right, I want to go through the play-by-play of what this homomorphism theorem for groups says. And there's a picture here, and I should tell you, full disclosure, these types of pictures are one of the reasons I fell in love with algebra. I love diagrams that communicate a bunch of information. So let's look at the setup for this homomorphism theorem for groups. So we've got G and H, they're groups, and we've got a homomorphism F from G to H. And in our picture, our homomorphism F from G to H lives right here. I'm going to assume that this homomorphism is onto, and one way that we can denote that with some decoration on our arrows is by drawing an extra arrowhead. So we have this sort of double arrowhead. That says that this is an onto homomorphism, which means that the image is all of H. We can get anywhere in H by plugging in stuff from G. And we're assuming that the kernel of this homomorphism is K. So K is equal to the kernel of the homomorphism F. Then we know that K is a normal subgroup of G, that we've already established, and there exists an isomorphism from G mod K to H, so that when I plug in an element from G, I can go either way around this diagram to get to H, and I'll get the same thing. So let me recap that. I've got the function pi sub k defined to say, okay, cool, I'm going to take my normal subgroup G and I'm going to make it into the kernel of this homomorphism from G to G mod k using the map pi sub k that we talked about before. So that guy over here, this is just a matter of definition. And what this theorem says is that if we need to build an isomorphism from one group to another, like let's say G mod k to H, if we can set up F and get a nice kernel for F and then just build that pi sub k map, this map right here, dot, 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 green arrow, exists and is an isomorphism. And one way to signify that that's an isomorphism is you can put a double arrowhead to say that it's onto and a hook to say that it's one-to-one. So in arrow language, in commutative diagrams, you'll see this for onto, you'll see this for one-to-one, or injective. And so if something is both one-to-one and onto, you get a double arrow with a hook. So this is a really, really cool theorem, and what it's saying is essentially that you've got some choice in how you go around this picture. So if I take an element here, take this element G, and I traipse along this way, I get f of G, whatever that happens to be. That might be something that I don't really understand that well because f might be complicated. But if I can figure out what its kernel is, what this is saying is that, aha, I can take G and I can also traipse around the long way. So I can come here and make a pit stop at pi sub k of G. And then I can use my isomorphism phi to finish up. And at that point, I've got phi of pi sub k of G. And I'm going to get the same thing, whichever way I go around the diagram. In the proof of this theorem, I want to just tell you a little bit about the big picture. This argument, where we pick an element and see where it goes, so we're going to follow it around, is something that is often referred to as doing diagram chasing. And that comes from the idea that we're taking an element and we're chasing it through these various arrows and seeing where we end up. Now, the big picture of this theorem, which is not something we're going to talk much about, we're going to use this theorem without worrying too much about its proof. But the big idea is that, first of all, we want to make sure that it actually makes sense to define phi to say that phi of a coset is the representative of that coset. So this is where we get into the idea of being well-defined. So the issue is that if x and y represent the same coset, we want to make sure that phi sends them to the same element of h, because otherwise we're not working with a function. We have the same coset, but we might try to send it to different places. So that's what this argument does right here. It goes through and it shows that, in fact, if x and y represent the same coset, then they have to go to the same place in h. The reason that works out is that K isn't just some random normal subgroup, it's the kernel. And so in the kernel, you recognize that you're going to get stuff that gives you the identity, and that's a trick that we use to show that this particular thing is well defined. So once we know that it's well defined, we want to make sure that phi is actually a homomorphism, and this step is checking that phi preserves algebra. So if I start with cosets and I end up with elements of H, I want to make sure that the operation on the cosets gets transferred over to H. And that's what that step does. The next step is checking that it's an isomorphism, which we're going to do in two parts. So we want to make sure that it's onto, and that happens because F is onto, so that allows us to do some tweaking here to make sure that we get a coset to go to the element of H that we want it to go to. And then we want to check that it's 1-to-1, and we use the fact that that K is our kernel. So if we can show that the only element in the kernel is the identity, then we know that it's onto, or it's 1-to-1. Sorry, misspeak there. And we're going to do this by showing that the kernel of this homomorphism, so the kernel of phi, is equal to the identity of the group G mod K, which is just the coset K, the kernel K. But that works out really nicely because K is the kernel of F, and so if we take something from K and we are expecting to get F of that thing back, we know we're going to get 0 in H. And then if we took something outside of the kernel and we got 0 when we plugged it into phi, that would mean that F of that thing, F of the representative of that coset, was going to be 0, and we should have put it in the kernel in the first place. So this is how we show that this is a that there exists this magical isomorphism phi that relates a group H to a quotient of a group G. And it's a pretty cool theorem. So this page of the notes gives you some advice about using the homomorphism theorem for groups. It says, let's say that we've got this abelian group G, and we're looking at a subgroup N of tuples in the Cartesian product of G. So we're looking at elements where X and Y are the same thing. So one way we might think of this is it's the set of things that look like X, X in the cross product G. And we might want to figure out what happens if we, like once we show that N is a normal subgroup, we might want to know, is there a way to think of G cross G mod N as some group we already know something about, right? And a good candidate for that is actually the group G. We could try to do this directly by actually setting up a function and trying to show that that function is an isomorphism, but that turns out to be a really hard problem in general. Instead, what we can do is we can set up a function from G cross G to G. So that's going to be our function f. Once we set up f, we figure out what the kernel of f is. And hopefully that will be our group N. So we're going to try to build a function f so that instead of k here, we get that the kernel of f is N. So we want to build f such that that happens. If we can do that, then we get pi n that takes us to G cross G mod N. If f is onto, then we automatically get this isomorphism phi that connects those two things. So this is a way of harnessing the power of the homomorphism theorem to show that two things are isomorphic when it might be difficult to build the isomorphism directly. And these are the details of that example. I've given you some to try in the homework, and I'm sure we'll have a chance to talk about those in office hours. But take a look at this example and let me know if you have any questions on Piazza. Another thing that might be relevant to try as we're getting closer to the end of the course here, I want to give you another homomorphism to play with. So think about the homomorphism, or the function, say the function from let's do z mod 6. I'm thinking of this as a group under addition to this fancy u sub 6. That's going to be the group of sixth roots of unities under multiplication. So right here, this is the set 0 through 5 mod 6. And this set on the other side is zeta 6 squared up to zeta 6 to the 6th, or 1. In fact, let me rewrite that a little bit. Let me write this as zeta 6 to the 0, or 1, and then zeta 6 to the 1, zeta 6 to the 5th. And the way that f works is I take a mod 6, and I'm going to get zeta sub 6 to the a. I would like to show that f is an isomorphism. And I'd like you to think a little bit about how you would do that directly, and then I'd like you to think about how would you try to use the homomorphism theorem for groups to set up a little triangle where I've got maybe z and then the roots of unity mod 6 and z mod 6 over here. If we write it as z mod 6z, that might give you some hints. So I want a function f over here. I want the kernel to be 6z. I want pi sub 6z to be the projection, or the quotient homomorphism, and then I want to prove everything I need to get this isomorphism phi that takes z mod 6z, or z6, to the sixth roots of unity. So that's another approach to this problem instead of doing it directly. And I think it's kind of fun to think about and ties together some of the things we talked about earlier in the course with some of these later concepts. All right, I will see you in class or on the screen in some kind of approximation of class. Hang in there, be well, and enjoy this algebra. There are lots of things going on in the world right now, but you're one of a pretty select group of people that understand some of this algebra stuff, so I hope you at least feel special about that.